In this video, we'll be looking at the limit comparison test. Now, unlike that of the comparison test, which we simply just have to bring a new series to the table and make sure that there's an appropriate comparison, the limit comparison test actually has two series that we compare using a limit. So we're going to have still a series a sub k and another series b sub k, such that, again, they still have positive terms. And then we're going to go ahead and look at the limit or some value k equaling to a limit, sorry, not k, I think we call it L. L equals k to infinity of a sub k divided by b sub k. So we're going to go ahead and talk about this value L. So the question is what does L end up being? And based on what it ends up being, what does that allow us to say? Now, the proof uses absolute definition of a limit as well as the comparison test to do so. We're not going to go over the proofs of all these conclusions. We're just simply going to go ahead and clarify them and then use them. So for this one, there are three real conclusions, which kind of sum up to simply be two conclusions, depending on how you look at it. So we have the first conclusion is that if I have L sitting between 0 and infinity, meaning if this limit is equal to any number other than 0 and any number other than infinity, then I can conclude the sum a sub k and the sum b sub k both either converge or diverge. What we're trying to say here is that the limit of terms of the ratio of those two values are going to a specific number, meaning that they're doing not necessarily the same thing, but they're doing it comparatively in such a way that if the ratio changes in some way, they either both are going to converge or they're both going to diverge. Again, the proof for this is really kind of heavy, so we're going to avoid going ahead and using it. If you want to see it, I can guarantee that there's other videos out there to see it. So that's the first possible conclusion. There again are two others. So the second conclusion is that specifically if L equals to 0 and the series that we brought to the table, b sub k, converges, then I can also conclude that a sub k, the series that we're looking at, will converge as well. So notice how this is slightly different. If I have L equals to 0, and I must have then convergency for me to make any conclusions about a sub k. The third statement actually correlates then to L equaling to infinity. If that limit ends up going off to infinity, and my b sub k diverges this time, then the summation of a sub k will diverge as well. So this is really your overall conclusionary statement about how things are going to pan out. It's a matter of, can I get this limit L to equal to a specific number, or does it have to be equal to 0 or infinity? If I get 0 or infinity, then I have to guarantee convergency for 0, divergency for infinity. So if my b sub k converges and I get L equals to infinity, then the limit comparison test is inconclusive and we're going to have to try something else. So again, this has some connotations with that of the divergence test as well as a couple of the other tests where we can't make absolute solid conclusions based on just what we've been given. We might have some low-hanging or some inconclusive conclusions, and we might have to try some other tests to make absolute conclusions in terms of what we're looking at, what we're playing with. So again, it's important to note that we can get a limit equals to a number. In this case, it doesn't matter what the series is that I brought to the table. If it's between 0 and infinity, then the series I brought to the table will always conclude the same thing as the series that we're trying to prove. It's when we get into this hairy mess down here where we get equals to 0 or we get equals to infinity that we actually have to be concerned.